that. The webinar this month was prompted by comments from previous webinars when we were asking for ideas, and also from questions asked of me after several seminars that I've conducted over the years. And the question is, what are the unique features one needs to consider when deciding on what type of boiler to be applied to a given application? It's a great question. And though it's not complicated in its answer, there are salient differences which distinguish a water tube boiler from a fire tube, making one or the other the best choice for a particular process application. It's therefore very helpful, I think, to have some fundamental ideas of the advantages and the disadvantages of each while developing a specification or a recommendation. So starting with a brief review of boiler types, we'll move into the uses of steam and typical industrial applications. And then we'll quickly move into the specific issues an engineer or a facility manager faces when deciding on the size and type of boiler that best fits their given situation. We'll then break these issues up into what I would call need groups. We'll give you, several scenarios. And in so doing, decide which boiler type best fits that given set of needs. Now, during this process, we'll also be looking at how the market is driving this industry, especially in the fire tube area, satisfying specific wants or needs which will enhance the customer's bottom line with regard to the overall cost of operation. Now, it's a very competitive world out there today, as you all know. And it's only those boiler manufacturers who listen and respond to the needs that will be successful. So let's get started. As mentioned, we are going to be centering our discussion today on steam boilers for the process industry and its typical applications. And in so doing, we'll be looking at the fire tube and the water tube boiler types, of which you can see here. We've got our fire tube, which then breaks down into various subgroups. We've got a packaged fire tube here. This would be a multiple pass. It could be 3 or 4 pass. We have single pass horizontal fire tube boilers. We also have vertical fire tube boilers, so they don't all have to be horizontal. Then we move into the water tube area, and that also breaks down into various subgroups. We have a package shown right here. That's about 300,000 pounds of steam per hour that can be shipped on a rail car or a truck, many tires on that truck, and it's a big one, but they can be shipped as a package. We also have modular type industrial water tube boilers that come in pieces with your drums, your headers, your manifolds, the pressure vessel itself, and the burner. But then they come together. So it's not field erected, it's a modular field erect. Then you've got commercial boilers, commercial water tubes. And then we've got, and those could be membraned wall, as you see here, that would be an O type. And then you have a flex tube water tube boiler. All of these are steam boilers, either water tube or fire tube type. Now, when we take a look at steam, what does steam really do? Why do we use this in a process? Well, the main reason for steam really is to provide a motive force. And as you can see in this old haystack 1700 boiler, what it was doing, it was driving this piston, which was driving a pump that was taking water out of a mine and pumping it out of the mine to somewhere else, rather than using donkeys and pails. Of course, also what revolutionized our country back in the 1800s, the steam locomotive, the boiler on wheels, the motive force that was driving these wheels, and this locomotive up to speeds that could exceed 100 miles per hour. Here's another example of the motive force of steam, these 26 fire tube boilers, many of which, at least half of these boilers had 6 furnaces, 3 in the front, as you can see here, and 3 in the back. But of course, what they were doing is providing steam, the motive force that would drive the generators, or the turbines that would drive the generators for electricity, and then of course the twin screws that was propelling the boat itself. So motive force of steam. The other application for motive force, of course, would be a steam turbine. Here you see the steam turbine, which is generating the power to drive a generator for electricity. But in many cases in our industrial applications today, we have combined heat and power, or combined cycle, you might refer to it as, wherein we are taking this steam, driving a turbine, which is then driving a generator, so we've got our electrical needs met. And then there's also parts of that steam that are being used for process. That could either be a motive force, it could be pressure that we need for that particular application, or it could be heat, it could be temperature. So, speaking of temperature, now we take that energy, that steam, which is really now being propelled by the motive force. So it's transporting those BTUs. That's the reason we have the steam. And now it goes into a heat exchanger, as you see here, the shell and tube, or a plate and frame, giving up that latent energy to the process, which could be a liquid, it could be water, or it could be a liquid that we are trying to heat for that particular process. Here's another example of absorbing that heat from that latent energy, or that steam that's coming in, which has the latent energy. I've got an absorption chiller. Or I could have a corrugating machine, which is now being used for corrugated box. I could have an autoclave, which would be used in the healthcare industry, in hospitals, for sterilizing instruments. Or it could be in the food processing industry, where I'm sterilizing food that's already been hermetically sealed in a can. Here's another application for steam, jacketed kettles. Maybe the pharmaceutical, possibly the food industry, where I'm reconstituting, or I am heating and blending a mix within that jacketed kettle. Another use for steam. And as far as industries are concerned, we are all over the place. Petrochemical would be a good example of where steam is used, either fire tube or water tube boilers. We're also, as I mentioned, in the pulp and paper industry. For fine paper, as you can see here, we could be in wood laminates, corrugated boxes, pulp and paper, a huge user of steam. We also are in microelectronics. You wouldn't think about it, right? But steam, of course, touches these circuit boards. It's what makes it happen. And then, of course, a big presence in the food processing industry. So steam is in many, many applications. Pharmaceuticals would be yet another one. The thing is that we are all over the place as far as steam is concerned, touches many industries. Many of the things that you see in the room right now, that you might be sitting at a table, a chair, whatever it might be, has been touched in some way by steam. The thing is that we've got a number of manufacturers that are using this and trying to control their costs for what I said in the very beginning is a very, very competitive market that we live in today as far as this world market. So controlling costs, and as you can see here, controlling the cost of fuel becomes paramount in terms of overall spend in keeping an operation going. So selecting the right boiler and applying it to that particular application becomes extremely important in trying to save this part of the pie that you see right here. So when we're looking at the type of boiler to be applied in a given application, what I've done here, and not in any particular order, I've just put down on the screen those particular criteria or issues that an engineer or a facility manager has to consider when deciding on what type of boiler to use. For instance, I've got a varying plant load. It doesn't just stay at a steady state all the time. It modulates. I might have seasonal fluctuations. Well, what does that mean? Well, it means in the wintertime, I've got a process application, but I've got a split load here. I use my steam for process, but I also use it for heating my building because I'm taking that steam and going through a secondary heat exchanger and heating the building that way. So I've got seasonal fluctuations when I go from winter to summer, or the shoulder months of spring and fall. I've got a large capacity. Do I tackle this problem with many boilers, or do I use one? I've got a very high steam pressure here. It's more than 150 pounds. What do I use? High quality steam. You know, I'm going to be taking that steam and I'm going to be going into a turbine. I've got to have high quality steam. I can't have a lot of moisture. In fact, I should not have any. What do I use? Oh, by the way, I've got limited space and I've got limited headroom. I'm going to be retrofitting within an existing building. How do I contain the cost here? And I've got a limited budget. And I've got to control the fuel cost. And I've got emission issues. And by the way, I want to take advantage of today's advanced controls. Okay, so these are the issues. What I'd like to do then is break them down into individual scenarios, and I'm going to have a total of 5. The first one will be, I've got a varying plant load with rapid swings. This becomes very important. It's a large capacity of 300,000 pounds per hour that I've got. And by the way, I've got very high steam pressure requirements. In fact, it's going to be around 500 pounds. And I need high quality steam, less than 1/2 of 1% moisture. And like everything else in this business today, I've got a limited budget. So what do I use? Well, in this case, because of the varying plant load and the rapid swings, those two things, I would automatically start to look at a fire tube boiler. The reason for this is the fact that a water tube boiler, as opposed to a fire tube, has less square foot of heating surface. It's been designed to have a high pressure density differential between its upper drum and lower drum. These riser tubes have been sized such to have adequate heat flux. In other words, more steam in the tube than water. And with the pressure density differential, I've got rapid circulation and tremendous heat transfer in these boilers. So when I've got a varying load and rapid load swings, my first consideration will be a water tube boiler. Because I don't want that pressure to drop, okay? As it begins to drop, I want to make sure that I modulate to that firing range to get the circulation I need to take the heat away from the burner and give me the steam that I need. The next thing that would favor a water tube as opposed to a fire tube in this particular scenario is the large capacity. In this particular case, 300,000 pounds per hour that I need for my process. And I'm going to be operating at pressures up to 500 pounds. Now, if you take a look at 300,000 pounds, that's about 7,800 horsepower. A fire tube is limited to about 2,200 to 2,500 horsepower as a package. These boilers go way up well over that. And we could be talking megawatts with water tube boilers. So now it's just a selection of either an A-type, a D-type, or an O-type, which would give me the 300,000 pounds per hour at an operating pressure that would be at least allow me to get to that 500 pounds. So you could have a 900-pound design pressure. The fire tube is limited to about 350-pound design pressure. So now because of the large capacity, because of the large design pressure, the high design pressure, I'm again looking at my water tube as being the best solution in this particular case. The other thing that we mentioned in our scenario here is we've got to have high quality steam. A water tube, because of the way it's constructed, with these internal baffles in the upper drum and additional dryer cartons that could be added, can give us 1/2 of 1% moisture, as opposed to about 1.5% moisture with a fire tube boiler, just standard. That means that with a fire tube, if I were to apply one to a application that's requiring high quality steam, I would have to have an inline separator within that steam piping, within the header piping, to trap the moisture. That would be a centrifugal separator. Adds additional cost, and of course, budget is a consideration in this scenario as well. The thing with a water tube, and I mentioned additional dryer cartons, we can take that moisture content, the quality of the steam can be 1/10 of 1% with these. So that would be another reason why I would begin to favor the water tube in this particular case. I mentioned that they could be driving a turbine in this application. The reason for the high quality steam, that's then driving a generator to generate our electricity. Many cases in those situations, they will require a superheater. What a superheater does is it takes the steam, it adds additional BTUs, and you do not increase the pressure, but you increase the sensible energy in that steam, thereby increasing the temperature. So at 600 pounds, my temperature, my saturated temperature of that steam is 485 degrees. I could add 300 degrees of superheat, still be at 600 pounds, and have a process temperature of that steam at 600 pounds of 785 degrees. The whole thing, the reason I'm adding this is I don't want that steam to condense in the turbine. Now, I can integrate I can integrate a superheater in a water tube. I can't with a fire tube. That would have to be an external superheater. Again, additional cost. Okay, scenario 2. Here we have a varying plant load, but it modulates. It's not a rapid swing. We also have a limited budget, and we have to control our fuel cost. These are the primary needs now for this particular application. What do? Well, I've got a limited budget, right? Well, right away now, and I see that I've got a varying load, but it's not, it's more of a modulating load. I'm starting to now think about a fire tube. Because a fire tube, on balance, is anywhere between 25, depending upon the type of boiler now. Is it a delta type? Is it an O or an A? And comparing with a fire tube, 25 to 40% more expensive. So a fire tube is a lot less expensive. The other thing is I want to control my fuel cost. What we have to understand is these water tube boilers are great in the right application. They're not as efficient, size for size, boiler horsepower for boiler horsepower, as a fire tube. The fire tube is going to be about 5%, minimally 5% more efficient than a water tube. That's why you see so many economizers on water tube boilers, to get that efficiency up. So when I'm looking at limited budget and I want to control my fuel cost, the most efficient option in this particular case is going to be my fire tube boiler. Now I've got a varying plant load. So the next thing I think about, and this could be applied on a water tube or a fire tube, but now I'm beginning to center my attention on a fire tube for the reasons I just mentioned. I've got a varying load, so now I've got to look at turn down, my burner turn down. Probably a 10-to-1 turn down would handle it, but then again, we don't know. We have to really understand the load, and this is where so many engineers and so many facility managers make a mistake. They don't fully understand how this load operates, if you will. So it could be that we may have to go not just with a 10-to-1 turn down burner, but also multiple units to be able to catch these loads at the various levels. And then to improve the overall efficiency, we may even be looking at adding economizers to these boilers. So now in our next scenario, we have seasonal fluctuations, limited space and headroom, limited budget, and we have to control the fuel cost, which is a key issue. And the seasonal fluctuations, that's not a primary concern, but it's got to be, part of the overall need selection. But the main things are limited space, limited budget, and controlling the fuel cost. At this point, what I'd like to do is apprise you and acquaint you of where the fire tube industry is going today. Years ago, when I came into this business, 5 square feet of heating surface per boiler horsepower was dogmatic, if you will. It was just a given. Today, with some of the modeling tools that we have available to us, and the expert engineering that we can take advantage of in this industry, we're getting away from that 5 square foot per boiler horsepower norm. What we're looking at, rather, are boilers that are smaller because our customers are asking for this. They're lighter in weight, and they're more efficient. Can you believe that, huh? What we've done, and it's by using computational fluid dynamics and finite element analysis, by doing this, we are able to construct boilers properly matching the furnace with the burner itself, with the furnace, and then the other heat transfer surfaces, convective and conductive heat transfer taking place in those areas. And match those properly so we can minimize the overall footprint of the boiler and not degrade its quality or its longevity. It still has the same life cycle analysis or life cycle time, if you will, as a 5 square foot boiler. The other thing that these engineers are looking at is properly designing and controlling these burners. What this graph right here is showing you is that we start off at 3% O2, excess air, or 3% O2 or 15% excess air. As we lose or increase that excess air to 5.8, I've lost about 1.5% in efficiency. The rule of thumb here is that for every 2% increase in excess air, every 2% O2 increase in excess air, we are going to lose 1% in efficiency. So we can't just design a very efficient package in terms of the heat exchanger without also paying equal attention to the burner itself. Now, what we find as being very typical in this industry are boilers that are operating in the 5.5 to 6% O2 range. But it's not at all atypical to see them up in the 7% range either, or as well. So why is this? Two reasons for it. Number one, the boiler's been oversized for that particular load. We didn't match the boiler to the load. The other thing is it could have a linkage system, an air-fuel control system that is not consistent. It does not repeat properly. It's got slip. It's got hysteresis. It's got problems. So our excess air level is rising. But the main cause is the fact that these boilers are spending time in this particular area of modulation, below 50%, cycling on and off, when they should be over here at the low excess air level and much higher efficiency. This is how they were sized, but this is what the load dictates. So what our engineers are striving for today is designing boilers that will hold that 3% O2 throughout the firing range. In other words, throughout the 10 to 1 turn down, or 4 to 1, or 8 to 1. Hold that 3% O2 so I'm not losing efficiency because of excess air rise. Just to show you what that means, here is a curve up on top where we have a burner which is holding close to that 3% O2 range. Here we have one that isn't. And you can see that as the firing rate from 60% of firing rate all the way back to 10, how the excess air increases in these lower ranges. And now added to that is the loss that is incurred because of cycling. Remember, every time that boiler cycles off, it goes through a post and a pre-purge. That's about 2 minutes of blowing ambient air through that unit and cooling it down. Now remember, those BTUs are derived from that burner because it's burning cash. Now every time you start purging air through those BTUs that were going into the water, you're cooling it down. Those BTUs and that cash is going out the stack. You want to limit that cycling. The other thing that we're looking at today in today's fire tube boilers are getting rid of the single point positioning systems. You see that you've got a single drive motor here. You've got a single shaft. That's now driving your fuel and your air. What happens is you start to get wear. You start to get stretch. You start to get hysteresis. And now you're not getting repeatability. You're not controlling that fuel-air ratio. Rather, go to parallel positioning where you replace all of that single point linkage with independent actuators that are then driven through a central control. Now I'm controlling my fuel, my air, and if I've got flue gas recirculation, I'm controlling that damper with this actuator. Now I've got repeatability. I eliminate the slip and stretch. This is the way to try to control on a repeatable basis that excess air very effectively. Now, as far as the burner is concerned, that also has to be looked at very closely because it's got to be matched properly to the furnace that it's firing into. And of course, you all know that for combustion to be complete, you need time, you need temperature, and you need turbulence. Well, as far as temperature is concerned, that's formed by the chemistry of the combustion process. You start with a spark, it lights a pilot, you then light the combustible mix, and from there on in it's spontaneous, the chemical reaction of combustion. That gives us the temperature. What about the turbulence? That's given by what we call a diffuser. So as the air comes through these fins, you have a turbulent pressure drop that picks up the fuel and mixes it. So now I've got my turbulence and my mix. But what gives me the time? You need time, you need temperature, you need turbulence for good combustion. The time is provided by the furnace. That's why this burner has to be properly mated to the furnace, so I have complete combustion within it. And then, once that chemistry has occurred, I've got my complete combustion, I now transfer the heat through radiation, conduction, and convection. And in these modern fire tube boilers today, as they are now evolving, the smaller ones, the lighter ones, and the more efficient ones, about 50 to 60% of the heat energy is absorbed in the furnace. That's very important, because that is the most effective heat transfer surface that we have. The balance, of course, is through convection. And everything is using conduction as well, because those high temperatures, that heat, transfers through the metal through conduction and then through convection on the other side. But all the surface that sees flame, that's radiant heat transfer, the most effective. The way we designed them before was we would have multiple passes, and we wanted to maintain specific velocities through these tubes. So you've got a plug of gas traveling at about 50 to 60 feet per second down this furnace. We then reduce the cross-sectional area to maintain the 50 to 60 feet per second. We reduce it again and again. So it is through this velocity that we are getting this turbulent flow down these tubes and not laminar flow. But what this did, it added additional horsepower. It added additional geometric size, if you will, to the unit, because we needed 3 or 4 passes to be able to absorb that heat. Today, what we're trying to do is get away from those plain tubes, which is what you see here. The design engineer, when he was designing this particular boiler, had sufficient velocity through the tubes. He had enough horsepower in that blower motor to be able to overcome the pressure drops. But still, there's a certain amount of laminar flow here at the, as the velocity begins to decrease, let's say from 60 to 50 feet per second, you begin to develop a boundary layer here. So that's now insulating the heat from the tube and that conductive action across the tube wall. I want to get rid of that. So now I go to extended surfaces. I can reduce my heating surface overall, because now with these extended surfaces, I can increase my heat transfer by as much as 85% more than I did with a plain tube. So now what I have is I've got a high ratio of inertial force as opposed to viscous force. In other words, my Reynolds numbers are high, between 3,000 and 4,000. I also have a greater heat transfer coefficient, which is the amount of heat I can transfer across an area based on its delta T. So all of these are better with this kind of design. So that's the way the engineers are going today. So far we've addressed space and fuel cost. But what about seasonal fluctuations? As far as the budget is concerned, if we take a look at seasonal fluctuations and also limited budget, let's look at the budget first. We've got the integral burner here on the upper left, and we have the gun burner or the packaged boiler here. In this particular case, this boiler certainly has a very appealing look. It's got front and rear doors that swing open. It's got advantages there. However, it's more expensive. So if we got a tight budget situation, my vote would go toward the packaged unit. They both are equal efficiency. They both will turn down. They both give you all those advantages that we looked at. There are some additional advantages here, but the juice is probably not worth the squeeze in this particular case. So when budget becomes an issue, my nod would go to the gun burner or the packaged type fire tube boiler that you see here. Now, what about the seasonal fluctuations? As I mentioned in the opening, we have these situations where we've got one boiler or several boilers that are handling a process, but then in the summertime that process continues, but the heating load does not. This is often overlooked by engineers and people who are involved in the selection process. What happens to that load throughout the year? Does it change? And if it does, it can certainly drive your operational costs. They can become a killer because of the cycling that goes on in the summertime. In the slide that I showed you earlier, these boilers were most efficient at about 60% firing. But I've seen many boilers which are most efficient in the 80 to 90% range, and once they go under or above the sweet spot, they lose efficiency. Now the key is sizing a boiler to the load that it is intended to meet most of the time. Now this can be difficult in the colder climates where we have a combination of process and comfort heating. But in these situations, when we shed the comfort heating in the summertime, the boiler often loafs along in the low fire range and well off the sweet spot and may cycle several times an hour. These are all very inefficient conditions. The fact that it's operating at the low fire area, higher excess air, and then of course cycling on and off. Now at this point you might say, well Steve, didn't you say there are offerings out there which address turn down and maintaining 3% O2 across the firing range? Yes, I have. And if you've got a boiler like that, and that turn down is going to meet that load in the summertime, God bless you. That's great. But if you don't, in 9 chances out of 10, 6 chances out of 10, whatever it might be, you don't, that boiler is going to be cycling. It's not going to have that turn down, and you're going to have the problem. So what do I do in a situation like that then? What I have found in the years that I've been involved in this industry, the best thing to do in this particular case is to go to a summer boiler. Yeah, bite the bullet and buy a smaller boiler for that particular load in the summertime, for that process load. And they come in various shapes and sizes. Here's an O-type water tube boiler. This particular one would slide right through a standard mechanical door, or a vertical, or a horizontal, or a flex tube, whatever it might be. These boilers can be the salvation in terms of overall operating cost when it comes to seasonal changes and considering a summer type boiler. Next scenario I'd like to address today will be the one that you see here, retrofit with existing building in a limited budget. Well, again, we're looking at boilers such as I just showed you. Ones that can possibly fit through that door without demolishing the walls, making the construction spend as minimal as we possibly can. That could be a boiler like this, or it could be a vertical. Could be a small horizontal. It could be a flex tube type boiler, a water tube. These can be field erected. It could be a cast iron sectional. But if it's a process load that's over 15 pound steam, then the cast iron won't work. It can come in sections, be built right there in the boiler room, but it only 15 pound is its limit. So if we got any pressure over 15 pounds, cast iron will not be applicable. But a flex tube would, or an O-type water tube would, or this vertical would, or this horizontal fire tube would. So think about that, because then all the boilers in the wintertime, that large process boiler is operating at the sweet spot all the time. And then in the summertime, the smaller summertime boilers operating at the sweet spot, saving bundles of dough as far as operating cost is concerned. Now our last scenario today that we'll be addressing is emission reduction and advanced controls. Now this could be probably a retrofit situation, let's say. As far as emission reduction is concerned, The industry has come a long, long way. We've developed and designed and applied low NOx burners, which will take, normally an uncontrolled gas burner will generate about 120 parts per million of nitrogen oxides. And that's what we're concerned about, because NO and NO2, nitrogen oxides, are the precursor to smog, to bad ozone, if you will. So we want to get rid of that. Low NOx burners will take that NOx just by themselves and firing into the right combustion chamber, into the furnace, reduce it from 120 parts per million down to 60, 40, maybe even 30 parts. But beyond that, and now the regulations are calling for more and more reduction in NOx, we may have to go to flue gas recirculation in conjunction with the low NOx burner to take us down to levels that could be sub 9 parts per million. Remember now, 120 to sub 9. Now we start getting below that, let's say 4 or 5 parts per million, or even less than that, we may have to go with selective catalytic reduction systems in conjunction with FGR. So now what we use, we could be using ammonia as the reagent, either anhydrous or aqueous, or possibly urea would be the reagent that we would use to break this NOx down to something that which would be relatively inert. So that would be selective catalytic reduction, with that ammonia then being applied to the catalyst, and it's across this catalyst therefore, that we get that reaction and reduce the NO and NO2 to inert gas. Flue gas recirculation is taking a certain portion of the gases before they exit the stack, blending them with the secondary air for combustion, increasing the temperature of the combustion air, but also at the same time what we're trying to do is cool the flame without quenching it. By reducing the flame temperature, we can dramatically reduce the amount of nitrogen oxides that are being generated by that gas flame. As far as controls today, we've come a long way there as well. What's really changing in a very, very old and very mature market, the boiler industry, is the amount of effort and the amount of changes occurring with combustion as far as the burners are concerned, and with controls. Our customers have come to us today saying, look, we want to communicate more effectively. We've got people out there that are maintenance people that are now taking care of boilers, and they're also doing multitasks. We've got to keep them aware of what's going on in that boiler room. So now with things like touch screens, we can take a look at what's going on with that boiler, what the operating parameters are, what the set points are, what the alarms are, what the alarm history is, and be able to communicate that not just within that building, but from, let's say, from the boiler room to the boardroom, or across the country. This information can be imparted. So it's all about getting control of what's going on, because remember, what I'm burning in this boiler is cash. And if I can save 2, 3, 4, 5% or more with fuel bills running well in excess in many industrial plants of $1 million, we're not talking about small change here. We're talking about big money. And so these controls can help us get there, because what they do is they integrate my flame safeguard or my burner management system along with my combustion control system all in one common PLC platform. Bring them all together and then be able to accumulate the information so I can react early rather than reacting later with a trouble call and downtime. So, in the final analysis with today's program, we've addressed 5 individual scenarios encompassing the typical need issues encountered in the process industry. And hopefully it gave you an opportunity to better acquaint yourself with these issues and how they would be best addressed when you are confronted with the cited choices. So in summary then, process boilers are found in countless applications spanning countless industries. Fuel's a major cost. Fire tube and industrial water tube boilers have distinct advantages and disadvantages. We should know those. Fire tube boilers are evolving, more efficient, smaller, and lighter. Holding 3% O2 across the firing range is now possible. And when budgets are tight, the alternative is the gun burner package. Understand the load conditions. I can't stress this enough. And consider a small boiler for the summer load. Keep those boilers running at the sweet spot as much as you possibly can. NOx reduction has arrived with FGR and SCR packages. And advanced controls for newer retrofit provide energy savings, improved reliability, and safety. So now let's open it up to questions.
Well, thank you very much, Steve. That was a great presentation. While we're waiting on the questions to come in, and if you do so, would you please direct it to all panelists using the question and answer tool on your WebEx control panel. We'll give everyone just a few minutes to get those questions submitted. While we're doing that, just a couple of announcements. At the end and the conclusion of this WebEx, when you close out, you will receive a survey. If you would be so kind as to fill that survey out. It is very important to us. We use that survey. We try to improve upon our effectiveness of giving the presentation and on the content that we have. So it is very useful to us. A lot of the information that we have put together for these presentations does happen to come from some of the suggestions that we get on the surveys. Would also like to thank the repeat attenders who have joined us today. We do have a record number of in attendance, and we're either doing a very good job of getting the word out, or you guys are actually telling other people about us. And if you are doing that, we are very grateful for helping us get the word out to others. And we do have a great number of questions coming in, Steve. This is looking really good. Also, we are giving out certificates for attendance. You can use these for your professional development hours. Most of you have indicated on your registration that you would like to have one. If you did not, it is not too late to do that. You may indicate so on the survey that comes to you at the close of this presentation. Next month's topic is deciphering the final EPA rules. We'll look at major source and area source final rules that were just released by the EPA. So be sure you go to our website at www.cleaver-brooks/webinars and check out next month's topic. Also, you'll find all of our archived events along with today's presentation. Today's presentation is recorded. You can have it in audio and video on the website, or you may download it as a PDF for your use. With that, let's go ahead and start with our questions. We do have an expert panel with us today. We have Earl Pfefferkorn and David Brick. Thank you so very much for helping Steve out. Steve does a great job of presenting, but he's also a great expert for us to have as well. So we just appreciate the two of you jumping in and helping out. Let me scroll back up and see if we can get some of these questions in. One of the first questions we had earlier in the presentation, Steve, and I'll let you or Earl or David jump in on this. The question is, a boiler has been proposed for our site without a boiler room. Our site is a chemical plant. Please comment on disadvantages of not having a boiler room and how we might need to compensate. And as a little bit of an added note, it says, FYI, the boiler is proposed as an outdoor boiler, no boiler room. We would run indications from some instruments to a control room some distance from the boiler. Can either one of you comment on that?
Sure. Both the fire tube products and the industrial water tube products have options to be mounted outdoors without a boiler room. A number of our customers do that. We have sites like that. The things to consider are, number one, we need to make sure that the controls are put in a weather-resistant, water-resistant type of enclosure, so the controls need to be properly set up for outdoor installation. The other thing that comes up is that the variation in ambient temperature can have effect on boiler efficiency. So there are control systems called O2 trim that can compensate for some variation in outdoor temperature variation. Otherwise, you would lose boiler efficiency as the temperature rises and falls. Again, that can be compensated in the control system. In some extreme climates, northern climates where the weather gets quite cold, we may run into some sort of combustion and concern over freezing of some of the equipment. Some of that can be addressed with heat taping, piping, but it may require a air preheater for the combustion side in extreme temperatures. So there's people that do it. It's easier to do in the warmer climates, a little more difficult in the colder climates, but options exist to cover it.
Thank you very much, Earl. We'll move on then to the next question. Talking a little bit more about FGR and how it reduces efficiency. Can somebody comment on that? How much does the FGR reduce efficiency?
I can handle that one, Susan. As far as FGR is concerned, if you are talking, well, let's say 20 parts per million, 30 parts or 60 parts per million, it's not going to affect the efficiency whatsoever. You start getting into some of these higher recirculation rates where we've got to take the NOx down to, let's say, sub 20, below that, you might be losing a bit. But it isn't very much. It's very, very small, because don't forget, you've got another gain here. You're taking some of that flue gas, you're blending it with the secondary air, so you're preheating that air. So you've got some BTUs that you're capturing there that would normally go out the stack. So the trade-off is very small. I would say less than, let's say, 0.5% at the very high end of the recirculation rates to get down to the lower levels, let's say 9 parts per million. The other thing is that in some cases, because you've got to have a good combustible mix, we may have to increase the excess air to compensate, because of the density of the flue gas that's coming in. The density of the air changes. So I might have to bring in a little bit more excess air, ambient air, and that's where I'm going to start to lose some of that efficiency because of the rise in excess air. But the offset is still there as far as preheating the combustion air. So let's say, you know, as a rule of thumb, maybe 0.5%, certainly not more than 1%.
All right, thanks, Steve. Next question. Does an SCR application affect the sizing of a forced draft fan? And could an induced draft fan be used to apply SCR to an existing burner without modifying the burner?
I'll answer that one. A very, very good question there. Basically, with an SCR, you're adding more complexity and ducting to the exhaust stream, and in that you do have additional pressure dropper restriction in there. And the answer is very straightforward. There is additional restriction. It would require more fan horsepower, but you can put a ID fan on the back side of it to create enough draft to use with an existing burner.
All right, thanks, Earl. How do you recommend sampling the water prior to it being put into the boiler in order to increase efficiency?
Well, we recommend sampling using a sample cooler. That can either be on a deaerator or feed tank, or it can be on the boiler itself. But normally it's on the feed system. Let's say it's in a deaerator, and then the analysis. They have test kits that will then be checking for hardness, checking for pH, checking for sulfite, I should say sulfate. And just, you know, checking for all of those things based on what the water treatment expert has recommended. Very important. This is not an area that, as far as Cleaver-Brooks is concerned, or even our worthy competitors get involved in very much. We depend upon the people like NALCO or the chemical treatment people to come in and make the proper recommendation. We can tell them what we will recommend in terms of conductivity within the boiler itself, not to exceed so many micromoles or whatever it might be, but then they take it from there and make recommendations on the amount of continuous blowdown and the amount of chemical treatment that has to be added.
All right, next question. We are finding it possible to achieve 3 to 4% O2 on low fire on the 4 WI series boilers. Do you foresee any problems with overheating the burner at these low excess air settings on low fire? I don't. These boilers, and you're talking now specifically about the 4 WI.
has been tested, and we're looking at pullback of that flame front to the diffuser that could cause it to burn up. It shouldn't, unless there's something else wrong. But the way it was designed, it should be able to handle the turn down to those lower levels without impinging upon the diffuser and causing damage to it.
All right, let's go on to the next question then. And this might need additional information, but if anybody can give some help on it. For just building heating, what type of boiler do you recommend for retrofit?
Again, that's a very generic question. In the building heating side, there's been a tremendous advances in boilers in the last several years from an efficiency standpoint. What's key here is to getting someone to assess the basic building. You have to determine if you're currently on high pressure steam, low pressure steam, or hot water, and basically it has to look at the size of the coils and the type of system that you have. But there is the opportunity either with a condensing boiler or some of the hybrid systems that we have available that mix some of the older systems and the new condensing for significant fuel savings on the heating side. But you would have to go out and take a look at the boiler room and at the building itself to determine what options exist out there. But the potential for significant fuel savings exists.
All right. Here's one concerning an application in a plastics plant where we need high pressure steam, 650 psig, but a very small load, approximately 7,000 to 10,000 pounds per hour. The steam does not need superheat. Do you have any suggestions for this application?
Yeah, we do. There are what we call commercial water tube boilers that are available out there today. Cleaver-Brooks has some. Some of our competitors have them as well, that will operate at those higher pressures and lower horsepowers. Normally they are either a coil type or a water tube boiler, a boiler as opposed to a generator. And that's how you would get to that pressure and be able to, in those lower size ranges. The flex tube that I showed, that probably wouldn't get up to those design pressures. However, that smaller little commercial water tube that I showed in the upper left-hand corner of that slide, that will get up to those higher pressures and allow you to operate, you know, the lower range as far as the horsepower is concerned, but the higher pressures. So there are options out there for you for that particular application.
Okay. Next question. Does Cleaver-Brooks provide the SCR package typically, or is it a third-party provision? If it's a third party, who guarantees the performance?
What Cleaver-Brooks has done on SCR packages, we have pre-designed SCR packages for all our larger fire tubes and our industrial water tubes. So we have worked with the design of the SCR package. We do use a third party for provision of the catalyst and some of the components, but we do have pre-designed systems, and Cleaver-Brooks stands behind the performance guarantees.
Okay. What are your suggestions, or how do you feel about using an economizer on a fuel oil only boiler?
An economizer can be certainly used when you're oil firing. You've got to be careful. I would assume you're talking distillate number 2 oil. If it's number 6 and it's got sulfur, then of course it raises the concern, because we'd be concerned about cold end corrosion here. But there definitely are economizers that have been applied to boilers that are firing oil. Sometimes the fin distance, you know, fins per inch might increase, or decrease I should say, and some of them even have soot blowers that would be, you know, attached to them to be able to clean them, or at least have access to them should they begin to soot up. Remember, the dew point of oil is probably in the 230 degree range. So you've got to watch dew point temperatures as far as that stack temperature is concerned to avoid the cold end corrosion, because the susceptibility of of cold end corrosion with oil is higher than that of gas. Natural gas condenses at about 130 degrees. So they are out there. There are designs to accommodate that, and certainly something one should look at if you've got a high degree of makeup and you want to try to take advantage of absorbing some of that latent energy that's just going out the stack and can be, you know, could be, or the temperature that's going out the stack, and put it into your feed water, whether you're firing oil or gas.
Okay, all right. Next question, are there increased levels of NO, NO2 due to a decreased level of oxygen? In other words, are the boilers still running lean at 3% O2?
No, no, they're not. As a matter of fact, that's an ideal level. And the reason that we manufacturers, and that's not just us, it's all of our competitors as well, will recommend 3% O2 is because if you start getting close to stoichiometric with zero excess air, you start to get into some real problems because you don't have any control over the ambient temperature, you don't have any control over the relative humidity, you don't have any control over the barometric pressure and the calorific value of the fuel. And all of these can put you into a very unsafe condition. So we set these burners to operate at 3% O2 or 15% excess air for that reason.
All right, and Steve or Earl, or David, here's a question we have coming in. I appreciate the products of Cleaver-Brooks, but I think all the products are for huge facility application only and not suitable like here in Qatar, whereas we are experiencing here at 46 degrees Celsius plus ambient temperature. How would you respond to that, Earl or Steve?
We can reply back. Again, in the slide presentation, we tend to show photos of a wide range of products, and they're not really to scale in the pictures in there, but the larger boilers are for large institutional and chemical type plants, but we do have quite a few boilers in Qatar, and they tend to be in the smaller sizes. We go down to approximately 500,000 BTU, which would be typical heating a 10 or 15,000 square foot office complex. So our products do have the full range out there from small to large. Again, I don't think we quite highlighted that within the presentation here today, but we do a tremendous amount of small facilities.
All right, we are at the top of the hour, but we will go ahead and take one last question. Please comment on the general trend for new buildings that space heating boilers are generally water type, not steam boilers, typically because steam traps are frowned upon. Are we missing something?
This is Earl Pepcorn. Just a couple of comments here. The steam traps have always been a subject of discussion because they require maintenance, properly maintained to keep your steam system functioning properly. But what we have basically seen from the heating application, especially in the northern climates, is a condensing hot water system runs much more efficient than a steam heating system. With steam systems, you're required to stay with the steel boiler due to corrosion, so you're going to end up with efficiencies in the 80 to 85% range maximum. With a condensing hot water boiler in a heating application, you can get up into the efficiencies in the 90-95% range. So the hot water heating side is being driven strictly from a fuel savings, efficiency, economy perspective is what we see.
All right, we still have a great number of questions that are in, and what we would like to do is take all these questions. We'll have our experts comment on them. We'll get back to you individually and have them posted on the website for all to see. I'd just like to remind everybody that you can get a copy of this presentation from our webinars page on our Cleaver-Brooks website. That's cleaverbrooks.com/webinars. You can get this presentation as well as all of our other archived events. And would also like for you all to check us out on Facebook, LinkedIn, YouTube, and Twitter to find the latest information that's coming across from Cleaver-Brooks. Again, thank you all for your time and for joining us, and for the ones that have stayed around to help answer the questions. Earl, appreciate it. David, thanks for being online. Steve, as always, a great job on the presentation, and we look forward to next month's topic, deciphering the final EPA rules. So until then, we'll see you next month then. Thank you all and have a great day.